This is chapter 31, and we'll look at several questions that'll help you with the concepts in this chapter. Huygens principle basically just says that each point on a wave front acts as a new source of wavelets. There's a couple of pictures here that kind of show that, but I think the better thing to show you is this animation. And you'll notice that as the sound, or better yet, let's do this with water. As the drops hit the water, you'll see a wave, and that wave kind of makes its way out. So every time there's a new drop, you get a new wave. So there's another one, there's another one, there's another one, and those come from each one of the drops. So I know it seems kind of crazy, somebody had to name that, but Huygens was able to do that. So he says each point in a wavefront acts as a new source of wavelets. So you end up getting that. For number two, as you get further and further from a point of source of waves, the wavefronts appear straighter. So you'll notice that this is a wavefront, and as we get further and further from that point, we're going to end up getting a straighter and straighter um, wavefront. You can think of this as if you're skiing behind a boat and you make a wave that first it's curved, but then as it kind of moves out, those wave fronts do get straighter and straighter and straighter as they go. For number three, it says when plane waves, so plane waves, not P-L-A-I-N, but P-L-A-N-E, that means flat. When flat waves go through a gap, they're actually bent. And it says the wavefronts will not change much if the opening is wide. So you don't see a lot of curve to these compared to when we have a very narrow gap. So the narrow gap makes that. You can see the same thing in the water here. You don't get a big diffraction event. You don't get a lot of the curving. You get a little bit more flat here and then some curving on the edges. But when you make that slit really small, notice you get a really nice curve. So we're comparing the shape of the initial wave coming in to the wave that you see when it goes through the opening. And all it's doing is the two sides are holding onto that wave and making it spread out. Here, those two sides are only really on the end, so you still get very flat coming through. Same thing can be seen here. For number four, when a wave passes through an opening, some of the wave is bent, and this phenomenon is called diffraction. So what they've done here is they've put a pair of scissors, just cutting shears like you would see at the barber shop or at the beauty stylist, and they've put them in water, and then they make the water vibrate. When they do that, you see the diffraction pattern that kind of comes around these. Really kind of cool. For number five, diffraction occurs in radio waves, X-rays, light, and electron beams. This is called an X-ray diffraction pattern. They've taken X-rays and they've illuminated or just put those X-rays on a crystal. And when they shine those X-rays on a crystal, you actually see the structure. And this structure, I think, is of DNA. So you can actually see the double helix structure as it goes through. And that's how they found out what the DNA is. FM radio waves are not received as well as AM radio waves in some mountain canyons because they do have a shorter wavelength. So AM radio waves, very long wavelength, so when they go through they can bend around things. Short radio waves like FM radio waves, they tend not to bend over canyons very well, so you don't typically get those as well. Waves diffract most when their wavelengths are very long. So if you have a long wavelength, you get a very large diffraction. Short wavelength, you don't get as much of a diffraction. An interference pattern is produced when two or more light waves meet, the crests of two waves meet, the troughs of two light waves meet, or light passes through two narrow slits. So we can kind of go back and look at that again. What we're going to do is we're going to put two slits here. We're going to move the slits over, and then we're going to make those slits a little bit more narrow. And when we do that, notice that the pattern that we see, in fact, let's move this back over this way. When the waves hit, you see a little bit different pattern over on the side. So you can see it there. You can also see this in sound. If you're an acoustical engineer, you end up with this pattern here that you can see. And depending on how far you space the two speakers together or far, far apart, you get some really weird wave type of movement. Same thing happens with light. We can actually make two slits for the light here, and we'll make those really small and then move this over a little bit. And we're going to add a little detector, and that detector will allow us to kind of see what the waves look like as they go through. We can also add a screen, and if we make these slits just a little bit wider here, We can allow more of that light to go through. Let's move the detector, and you should see some different bands on the screen. So we get a really intense band here in the middle, and then on the edges you start to get a little bit lighter bands, and then you have dark bands here too. So that all happens when you get an interference pattern. Constructive interference is when you have two waves overlap and the crests are at the same point in time. So notice that this one goes up at the same time this one does. This one goes down at the same time this one does. And what happens is we will add the two waves that you see here to make this much larger amplitude wave. And then the trough will go down. Notice this one's about 1 1/4. This one looks like it's probably about the same amount, 1 1/4. And so we should get somewhere around 2.5 boxes for the trough and 2.5 for the crest. For number 10, destructive interference is the opposite. I have one wave going up, one wave going down, and when they meet, they actually make a very flat line. So we've destroyed them. That's why they're called destructive interference. For number 11, interference can be shown using water, light, and sound waves. So we've seen it here with light. We've seen it with sound. You get this really funny pattern here. And we also saw it with water. So we do see those with all three. A diffraction grating is just a really small piece of maybe cellophane or plastic. We've got some goggles that you're going to actually wear so you can see this. And when you put them on, the little tiny slit spacings actually make the light interfere. And you end up seeing these really kind of cool colors from where they're all split out. Number 13, when monochromatic, now monochromatic light is light that is of one color. When it goes through two very closely spaced slits and onto a screen, the pattern on the screen has alternating light and dark bands. We can see that with this again if we go back to light, and we see those light and dark bands over on the side. I can actually rotate the view here. Oops, can't do it with this one just because of the screen that we have on the side, but we can change some of the things and you can see the graph of kind of how intense this is. So we have a really intense middle part, and then as we move this back and forth, we can also see a little bit more. Here, let's make this a little bit stronger. We can see some of the bumps that come out from the interference pattern that's formed by the two slits. You see a really big area here of a really bright light in the middle, and then we get some dimmer lights on either side, and that's called an interference pattern. You see that same pattern right here. Number 14, monochromatic light is light of one color. We talked about that earlier, so you have different color lasers. Blue laser is the most powerful, green is the most annoying. This is actually close to ultraviolet, so this one's probably more powerful than this blue one is, and then red isn't as powerful. All these could blind you, so you have to be very careful with them. If you shine a laser light onto two plates of glass, one on top of the other, you'll see dark and light fringes. The reason that you see this is you get reflected light from one plate interferes with light from the other plate, and so it's just an interference pattern. For number 16, if you work for a telescope manufacturing company, you can actually test precision lenses for flaws. You place the lens on a really flat piece of glass, you illuminate it with a laser, and then you look for fringes. This tells you that if you see a lot of fringes, you will see a lot of different aberrations is what they call them technically, but you see all these lines and this fuzzy aspect. When they did this for the Hubble Space Telescope, they actually gave it quote-unquote glasses, and it made it see a lot better. It got rid of all this nasty interference that you started seeing. For number 17, you have a thin film. It appears blue when illuminated with white light. The color being canceled is yellow. Remember, the opposite of blue, this goes back to color when we did it last chapter, the opposite color is yellow. So that's just a complementary color. Colors when seen when gasoline forms a thin film on water is what we call interference. So we're actually getting interference patterns of light, and so you see these what we call iridescent colors. For number 19, iridescent colors seen in the pearly luster of an abalone shell are due to interference. So these colors, really pretty colors, are all the interference that are happening on the shell. This is a quarter, so you kind of see how big the shell is. But the thickness of the clear coating on the inside gives it the really kind of cool colors. People like that. Number 20, gasoline. If you've ever seen gasoline dripped on a wet pavement, you end up with this kind of thing. This is called iridescence also. So you see iridescence here in the shell, and you also see it on the other one. For number 21, holograms exist because of two things, both diffraction and interference. You can actually use lasers to make these, kind of neat. This is a real life hologram that somebody is projecting, and then this was seen in Star Wars, a 3D hologram. For number 22, magnification can be accomplished with a hologram if you view it with light that has a longer wavelength than the original light. So if you remember the refraction along wavelengths, you end up getting a bigger image. For number 23, coherent light is many different rays of light all having the same frequency, the same wavelength, the same phase, and direction. So a laser is coherent. It is in phase. So that means that all the light goes up and down at the same time. It's monochromatic. It's one color. This is an LED. New TVs are using LEDs and instead of LCDs. And they are monochromatic, but they're not in phase. You see that they're out of phase. They all have the same frequency, wavelength, phase, and direction. So these are all going to the right, we could assume. For number 24, light emitted by a laser is coherent. For number 25, this is the last one, I think. A hologram is most similar to a diffraction grating. So if you remember the diffraction gratings, they split out the light. A hologram does the same thing and gives you a 3D view of something that's on a 2D surface. And that is it.